Yeah? Okay, do you get the idea? Okay, so first of all, find the function which is buried within it, and then just differentiate each part separately, and then multiply them all together. But are you happy? This is quite tedious. This is quite long. Okay? Is there a quicker way? Well, let's look at the patterns. If we can see the pattern, then we can try and generalize. Well, let's have a look at this one because I think it's slightly easier. So I said, in fact, let me just rewrite this slightly because remember this 12 came from 4 times 3. So let me just write it again. So I'm going to write it as 4 times by 3, okay? Just to make it a little bit clearer, okay? Remember where we started. We started with y equals 3x plus 4 all raised to the power 4, okay? And I ended up with dy by dx equals 3 times 4, lots of 3x plus 4 all raised to the power of 3, okay? Can we notice a pattern? Can we notice what's actually happened here? So, first things first, we need to have a look at the two functions separately. The way which I remember the chain rule is as the Outy-Inny rule. Okay, the Outy-Inny rule. And here is why, and see if you can follow this with me, okay? First of all, I differentiate the outside function, the Outy function, if you like, okay? So the Outy function is to the power of 4, the something to the power 4 bit. See that? The something to the power 4 bit. If I differentiate that and leave the inside function alone, in other words, leave the 3x plus 4 alone, would you be happy? Let me write it down here. Would you be happy if I just differentiate the outside function, leave the inside function alone, I bring the power down, so I bring the 4 down, leave the inside function alone, and reduce the power by 1. Did you all see that? Yeah, so I bring the power down, becomes 4, reduce the power by 1 by 3, leave that inside function alone. Don't care about that at this stage. Is that okay? So differentiate the outside function, leaving the inside one alone. That's basically the same as when we let u equal that. It's just u, I'm just leaving there. Okay? And then the inny rule, the inny bit, I then multiply by the derivative of the inside function. Do you see that? So what would the derivative of the inside function be? 3. And then once I tidy it up, that's where I get my 3 times 4 from. So 12 lots of 3x plus 4, all raised to the power of 3. Is that okay with everyone? Okay. Let's just make sure it works with this function over here. Just make sure it works with this function over here. So my inside function is my 4 root x plus 7x. My outside function is the something to the power of 3 bit, the bracket to the power of 3. Okay. So let's check. Let's check. First of all, it should be the case that I differentiate the outside function. I do the outy bit, okay? So if I differentiate the outside function, I bring the power down to become 3 and reduce the power by 1 to become 2, leave that inside function alone. Make sense? Then I multiply by the inny bit, the inside function. So the derivative of the inside function is going to become, well, once you differentiate 4 root x, are you happy it becomes 2 over root x? Hence I get the 2 over root x bit. And once I differentiate the 7x bit, I get the 7. That's the derivative of the inside function. Does that make sense to everyone? Yep. Yeah? So actually, you don't have to go through this whole process. You can just do it in 1 or 2 lines if you need to. Make sense? And actually, once you've spotted the pattern, this will extend to as many functions as you possibly like. As many functions as you like. So I could have 3 functions all buried within each other, or 4 functions, or 5 functions. It doesn't matter. Okay? Can I talk you through another example? Okay? So just remember, the chain rule, another word for it, or another name for it, the Alex special name for it, if you like, is the Outy-Inny rule. Okay, just think, chain rule is just the Outy-Inny rule. Differentiate the outside, leave the inside one alone, then multiply by the derivative of the inside. So let's have a go. I mean, by the way, if you want to go through the u process, if you want to like set u equal to something and then go through the process which I got you to at the start, that is fine as well. It's just long. And who likes long things? Okay, good. So let's have a look at something like this. Let's suppose that my function, I'm just going to change the notation because I feel like it. Okay. Let's suppose my function is sine of e to the power of 2x. Okay. Sine of e to the power of 2x.
Is that n or x inside braces?
X. Okay. So sine of e to the power of 2x. So following my rule, if I want to find the derivative, so f prime of x, if I want to find the derivative, okay, I should differentiate the outside function, leaving that inside one alone. My inside function is the e to the power of 2x bit. Okay? What's the derivative of sine?
Cosine.
Cosine. So I differentiate the sine, leave the inside one alone. Okay? Then I multiply by the derivative of the inside function. But are you happy now that there are two inside functions? There's the e to the power of something, and then there's the 2x bit. That's the inside function. Doesn't matter which one I multiply by next. Shall we just multiply by the 2x bit? The derivative of 2x. Yeah? So what's the derivative of 2x?
2.
2. What's the derivative of e to the power of something?
E over x.
E to the power of something. Make sense? That's it. So I get 2 e to the power of 2x times by the cosine of e to the power of 2x. That is it. That is it. So actually here we had three functions. We had the sine, we had the e, and we had the 2x. And we just multiply by the derivative of each one successfully, leaving that inside one alone. We just work from the outside inwards. Is that okay? Right.